Next, I will show the result of the control analysis that has been done. The control theory has been applied on the one-bank model, which is described by these differential equations. The one-bank model contains only three quantities: cash, deposit, and investment. The one-bank model allows one to easily appreciate how the banking system has been modeled. Moreover, it is easier to investigate the effect of extraordinary signal, which is deposit, on the bank's cash and investment, since there are no interbank borrowing and lending effect. Importantly, the one-bank model allows a simple and analytical implementation of the stability analysis, which can be used also for more complex multi-bank model. The control analysis will follow the 4 steps below. First, find the equilibrium point of the one-bank model. Then, linearize the model around the equilibrium point. Design the controller based on the linear models. And the last is to test the design controller on both linear and nonlinear models. In the following slides, these 4 steps will be analyzed. The equilibrium points are those values of the state variables in which their first derivatives with respect to time are 0. Frequently, the behavior of the nonlinear model within a certain operating range of an equilibrium point can be reasonably approximated by that of a linear model. One reason for approximating the nonlinear model by a linear model is that by doing so, one can apply rather simple and systematic linear model design techniques, such as root locus analysis. The behavior of the solutions of the linear system are expected to be the same as the nonlinear one, so that a controller design based on the linear model will perform well also on the nonlinear model. However, it needs to be stressed that a linearized model is valid only when the system operates in a small range around an equilibrium point. In the one-bank model, by setting the derivatives of the Ci and Ii to 0, the equilibrium point can be identified. In this analysis, it is assumed that D1 and Op1 are kept constant in a given simulation. The equilibrium point are then found from these 2 equations, which can be solved under 3 different cases. Equilibrium point 1 is found in case 1, in which the bank is in a condition where it has enough cash, but it can only add investment determined by investment opportunity. In case 2, where equilibrium point 2 is found, the bank has again enough cash and will invest as much as it can, since the investment opportunity is larger than the available cash. In case 3, the bank doesn't have enough cash to invest, and the only equilibrium state consists of 0 values for C1 and I1. Based on 3 equilibrium points, the linearization is performed using MATLAB and Simulink, and 3 linear models are derived. In the control design for the one-bank model, the objectives are established according to the level of the cash the bank holds at a given time. 3 zones are defined according to the level of cash the bank has, as shown in this figure. The cash of the bank changes with time, and the bank can either enter different dynamics that are characterized by different linear models. In the first region, the cash is above the reserve ratio requirement, which satisfied the conditions shown in case 1 and 2. So this dynamic can be described by linear model 1 and 2. The bank is considered to stay in a safe zone under this dynamic. So the aim of the control is to keep the cash at a desired level that allows the bank to generate more profit. In the second region, the cash is below reserve ratio requirement, but still positive, and this satisfies the condition shown in case 3. Therefore, this dynamic can be described by linear model 3. Under this dynamic, the bank is considered to be in a dangerous zone, since it cannot meet the reserve ratio requirement. In this dynamic, the aim of the control design is to try to adjust the cash to meet the reserve ratio requirement. In the third region, the cash at the bank becomes negative, and the bank stops all activities. This can happen when a shock in the deposit is big enough to make the cash negative. It is assumed that the bank faces a serious funding gap, and if the bank does not take action to get more cash, it will fail. So the aim of the control is to try to bring the cash from negative to positive within a very short time. Before showing the control design, I want to give a brief introduction of the state space model, which is often used in control theory. A state space model is a mathematical model of a system whereby the input, output, and the state variables are related by ordinary differential equations. A state model is used because it can deal with a system that has more than one control input or more than one output. So in the analysis of the one-bank model, the system is a single input and a single output system. This method still can be used, and it can build up a good foundation for the future analysis. Another reason to use the state space model is that it is particularly well suited to the use of computer techniques, which enhance our ability to take the advantage of the computational efficiency of MATLAB. A general state space model is shown like this, where the x is a column vector that represents the state variables. It contains n elements for an nth-order system. X dot represents the time derivative of each state variable, which is also a column vector that has the same size as x. U represents the control input variable. Since the output feedback is used, the control input variable U is a function of the output Y. Here gamma is the feedback gain. In the one-bank model, the cash C1 and the investment I1 are the state variables, and output is the cash C1. Matrix A will be different for the 3 linear models. The aim of the control design is to design the matrix B and find out suitable value of gamma. This figure shows the configuration of the feedback control design for the one-bank model. The bank buy or sell its investment to adjust its cash to the equilibrium value. The error signal is the difference between the equilibrium cash value and the actual cash value. Depending on the strategy used by the bank to adjust the cash, 2 input distributions are developed. In the first strategy, the controller always tries to bring the cash to the equilibrium value by selling the bank's investment when its cash is higher than the equilibrium point, and adding investment while its cash is lower than the equilibrium point. In the second control strategy, the bank sells its investment when its cash is lower than the equilibrium point, and add investment while its cash is higher than the equilibrium point. After the controller U is set, the next step is to find a proper value of the feedback gain gamma to make the closed-loop system stable. In the control theory, the performance of a feedback system can be described in terms of the location of the roots of the characterized equation in the S-plane. Then the different controller has been designed based on different linear models, and the proper feedback gain can be selected according to the different system dynamics to make the cache to reach a desired value. Here the figure shows the simulation result in a case that as the cache of the bank changes, the nonlinear system switches between different regions and the controller switches accordingly. The initial condition of the simulation is when C1 equal to -15. The aim of the control is to bring the cache to a desired value which equals to 45. The system starts in region 3 and the bank's cache is brought from -15 to 0 within a very short time. Then the system moves into region 2. Therefore, the controller is switched. By continuing setting the investment, the bank's cache is brought to the reserve ratio requirement, which is equal to 20. Then the system moves to region 1. It takes a long time to finally get the system to a steady state with the desired cache value. In the last part, I will summarize the work, draw the conclusions, and discuss the future work. A model based on differential equations has been developed to study the banking system stability as a function of link rate, reserve ratio, deposit shocks, and the heterogeneity of the bank size. The Simulink block diagrams of the dynamic network model has been developed. The result of numerical simulations provided the insight of the dynamics of the banking system. It is the first time to apply the control theory to access and preserve the stability of a dynamic model representing the banking system. This thesis represents a first but yet important step towards the combination of network models of the banking system with control theory. It should be now plausible and desirable to apply control theory to better understand the stability of financial systems. One direction for the future work is to look for the use